Good afternoon, everyone. My name is Xinfeng Wang, a PhD candidate at the University of Yamanashi. The paper I want to share today is NFARec, a negative feedback-aware recommend model. So the recommendation system has become inevitable daily applications in our daily life. And the goal of the task is to find the items that the target user might be interested in given historical interactions of all users, so the system can assess the similarity between users to make a recommendation. And recently, the graph neural network has showed powerful performance in this task. The goal of they build the feature vectors based on multiple contexts such as spatial, temporal, sequential contexts, and the interaction signals. After that, they perform the message passing based on the interaction graph and match the figures of users and items and rank them to make a recommendation. However, they always ignore valuable information of negative feedback in two aspects. The first one is that even for the same items, the users could have opposite opinions which hide the optimal message passing option. For example, in the graph A, the vanilla GCN propagates information only through the connectivities between users and items, so they regard these two paths equally for message passing. However, let's see the figure B. In this interaction graph, the user U1 and the user U2 are both similar to U3. This is because they both give positive feedback on the I3 and I6. So if U3 will give a positive feedback on I4, then the red path should be the optimal path to passing the messages. However, if U3 give a negative feedback to I4, then the blue path should be the optimal path. So it suggests that the feedback is a very important clue in guiding the message passing of GNN. And the second issue is that even though some issues diverge from a user's preferences, then the user might still try it and provide a negative feedback. So to solve these issues, we propose solutions. And to perform the optimal message passing in GNN, we propose a novel hypergraph convolution operator that leverages the high-ordered feedback relations to improve the message passing of GNN. And to enhance the modeling of sequential patterns, we incorporate an auxiliary task, which is to predict the feedback sentiment priority of the next interaction, which is positive or negative, based on the transformer-Hawks process. The transformer-Hawks process excels in modeling the influence of past events on the current event, which is past interactions on the current interactions, whose impact diminishes over time. So based on this, we propose the negative feedback-aware recommend model, and this figure shows the overall architecture of this model, and the input is the user's historical trajectory, and based on those trajectories, we can build the use item feedback graph. And on one hand, from this graph, we can get the user's sequential patterns, and it taking into account the feedback. And after that, we use this model to learn the sequential representations. And on the other hand, based on the feedback graph, we can construct the user's structural patterns, which also consider the feedback in the graph. And then we use this model to learn the structural representations. After that, we use the decoder to get the probability distributions of candidates. So I'll explain these two models in more detail. In the sequential representation learning modules, we learn the representations through transformer-Hawks process. At first, we use stacked transformer blocks to get the hidden representations, and we use the output of the last layer as the hidden representations. After that, we use sampling to get the sequential representations. And then we enhance the representations with the auxiliary task, which is to predict the sentiment priority of the next interactions. So the objective function is given by this. It includes the interaction log likelihood and the continuous log likelihood. And the interaction log likelihood includes the cumulative sentiment influence here the Z means it is a positive or a negative, which is computed by this intensity function. So intensity function is to know how much is the probability of an interaction occurrence, which is positive or negative, according to the current state and historical interactions. So based on this, we can get the sequential limitations, and then I'll explain the structural limitations. In these modules, we propose a two-part hypergraph convolution paradigm. The first step is to model the interactions between users and items based on the interactive hypergraph convolution, as shown in here. And the second step is to perform the feedback-guided applications to enhance the massive passing of hypergraph convolutions through the optimal path. For example, the blue arrows and the red arrows shows the high-order feedback relations between the nodes. So in the interaction hypergraph, at first we perform the hypergraph convolution layer by layer, given by this. Here the script edge means the hyper edge, and this is the normalized genesis matrix, and the activation function, and the initial embedding matrix. After that, we can use the average pooling to get the user structural limitations, which is before we take into account the feedback relation. So the second step is to consider the feedback-gated applications. There are several situations we need to consider, which are opposite feedback, multiple feedback, and multi-hop feedback. So we need to construct the high-ordered feedback relations, squared x, and each element of the initial squared x is given by this. And here the theta equals 1 if you give a positive feedback on I, and it will be -1 if you provide negative feedback on I. Otherwise, it will be 0. And after that, we can get the high-ordered feedback relations based on the initial feedback relations, and then we can perform the message information aggregation. Here the head square x is the summation of different order of the feedback relations, and then we can use average pooling to get the feedback-aware user structural limitations. So the final leading score is given by these 8, taking into account the sequential limitations, the structural limitations, and the feedback-aware structural limitations. The SEQ is obtained through the inner product of sequential limitations and item embeddings, and the JI1 is the inner product of the structural limitations and the item embeddings. And then we use NLP to decode the feedback-aware structural limitations. And we conducted experiments based on 5 public datasets, and we compared 12 baselines for comparison. And this is of our performance of the proposed model and the baselines. And the bold forming shows the best performance, and the underline shows the second best result. So as we can see in the red part, the proposed model exceeds all the baselines, and we also conducted a 10-trial t-test to show that the performance is statistically significant. And the blue part shows the quantitative result. As you can see, the graph contrastive learning-based method and the method that learns both sequential and graph-based features are competitive among the baselines. And also, we conducted ablation studies to see which modules are effective. As we can see in this this table, the result SE means the result of the sequential limitations. As we can see, the sequential limitation boosts performance for all datasets, and the GIE means the structural limitations without feedback information. As we can see, on some dataset without the feedback information, the structural limitations sometimes make a limited contribution, and on some cases it even makes the performance worse. But if we take into account the feedback information, the structural limitations contribute to the performance for all datasets. And also, it is interesting to know which orders of feedback relations are effective. As we can see in this table, the optimal performance is achieved with different orders for different datasets. For example, the one order is best for recipe and the book dataset, and the second order is best for Yelp, movie lens, and the beauty product dataset. And also, we find that excessive high-order information will diminish the lower order signals and finally affects the performance. As you can see, when we add the orders into 3 or 4, then the performance will getting worse. And also, we visualized the user structural, sequential and structural limitations. The upside 3 figure shows the distributions of users' sequential limitations, and the downside 4 figure shows the user structural limitations. As you can see, both the sequential and the structural limitations can reveal which users are similar but reflect different aspects, because the cluster of users shows different shape and different distributions. And also, we find that the structural features stress more cohesion with cluster, while sequential features exhibits greater dispersions. So we can see the structural features can better learn the similarity and the differences between users, while the sequential features can learn more uniform representations, and it can help to mitigate the issues of some inactive users between isolated nodes. And also, we conducted case studies, and we find some cases that our proposed model achieved success, whereas the baselines fell short. For sequential limitations, when most of the ground truth candidates are with negative feedback, the proposed model works better, and if a user have a long historical interaction sequence, this is because the transformer Hawks process is good at modeling the long-term dependencies between in the sequence. And for the feedback-aware structural limitations, we find 3 cases. Users exclusively visit a place with high scores, and users actively explores new things, and a user is involved in intricate interaction networks, and our model works better than baseline. And finally, I will make a conclusion. We propose an NFARec model that maximizes the utilization of negative feedback in sequential and structural patterns. And we propose a novel hypergraph correlation operator that leverage high-ordered feedback relations to improve the message passing for GNN. And also, we incorporate an auxiliary task, which is to predict the feedback sentiment polarity of the next interaction. And in the future, we will explore the impact of implicit feedback to improve performance, such as user escaping some contexts. And we will try to incorporate the large model to make more interpretable recommendations. And also, we have released our source code and data. And thank you for listening.
Thank you for the presentation. Any questions?